using high resolution data and the machine learning for the area of transportation safety analysis. So I think like for both attendees, not only for the transportation or specific for safety, but but also for other fields. So I would like to say I hope like for this discussion, like for like can help or like more sharing, like if you have same data format. So first of all, I would like to introduce like what is transportation safety analysis. So in general, it will be divided into 3 levels. So first of all is about micro level crash analysis. So for this level is a very high level. It's focused on like zones, such as the transportation analysis zones, which is used for the transportation planning. So we are dedicated like for the long term, like several years, to see how many crashes will happen in the in the future. So we're trying to understand the impacts of like social characteristics, such as like a population by ages, gender, education, etc., or the transportation demands and the network attributes like the proportion of freeways or arterials, or the thing and pavement condition. So all the things, so give the object is trying to provide planning solutions such as education or enforcement to reduce the crash counts. And then in the second level is meso level, is trying to analyze the number of crashes happened in a segment or intersection on the roads, like still on the long term, like several years, and trying to understand the influence of the geometric design, lighting, or traffic flow on the crash occurrence. So with the object, like we can reduce the crash by offering engineering solution, such as hidden lighting or like wider the roadway length. And the third level will be the micro level, is we're trying to predict the crash at the segment or intersection, but it's a very short term, like in the next 5 or 10 minutes. So within this insight, we want to provide the ITS controls, like a variable speed limit to harmonize the traffic, or queue warning to send a warning message to the upcoming drivers, or like signal controls to harmonize the traffic at the intersection. So in the following introduction, I will introduce each of my research in the 3 levels separately. And also we know, we kind of experienced like big data revolution. And in the transportation field, we actually, the data for the transportation is like expanding like spatially and temporally dimension. So for example, for the spatially point of view, we'll have more detectors on the roads, like detect the traffics or speed or traffic or things. And also we have more coverage like by using floating car, always traveling on the roads like Google. So also we are expanding like temporally, like we only have the data aggregated like hours or like daily or years, but now we have data like minutes or even second. So with this like expanding, we can also, it's an opportunity like we're leveraging with this kind of big data and to do the analysis to better understand like the traffic occurrence and for the prediction. So here is some example like our like more and more traffic detectors. Like traditionally we have the loop detectors, like also have signal timing data, pedestrian call, and now we have like Bluetooth we can provide in the travel time along the segment, or the CCTV cameras. We can get the trajectory from each vehicles or the pedestrian on the intersection. Also, we have CCTV camera on the roadway to detect, and like microwave detectors to detect each vehicles along the freeway or ramp. And recently, we also have like availability of the video or like drone data. We can monitor the whole intersection to track all the vehicles, to get each vehicle's speed and identify what type of the vehicles by like each one and by each by each second, etc. So within all this, I will trying to introduce how can we use this data for the traffic safety analysis. So firstly, it's about the micro level transportation safety prediction. So traditionally, for this prediction, we are trying to, based on like a zonal level data, like how many traffic in total in this zone, and like how many freeways and how many arteries on this zone, to develop a statistical model such as a Poisson family model, Poisson model, negative binomial model, and to predict how many crashes will happen in the future. Also, we're leveraged by this aggregated data while using like a normal neural network or spot vector machine, like kind of machine learning techniques to predict. So as I mentioned here, we just will use data like traffic data, roadway information data, and the social demographic data. But all this data will be aggregated at a zone level. So here is an example. As you can see, on the left side and the right side is we're trying to aggregate the information about speed limit on the two of zones. So within that, we can get a proportion of zone roadway with speed limit lower than 30 miles per hour, or between 30 miles per hour to 50 miles per hour or over. So although we can see directly from the two pictures, actually the roadway structure or the speed limit distribution is quite different. But with this kind of aggregation, actually by these three variables, we will get the similar values. In other words, we lose some information by this aggregation process. So, so in that case, how can we like using the deep learning method or like using the big data to avoid this kind of information loss? So this is, I'm trying to use the convolutional neural network. So as we know, convolutional network is very popular especially in the image recognition. So by understand each information from the pixel level in one image, it will understand like what is can detect. So what is in the picture, like a dog, identify dog, or like a cat. It is a very famous example. So actually, the CM model is very powerful to capture the spatial interaction between each pixel level and to contain information with a very high resolution. But for our transportation level, like micro planning, so the road, the information is mostly in the map. So then I trying to, based on the structure of the CN model, to propose a method to locate all this kind of information to the pixel level. So here is the example of the intersection. So intersection is actually in the map is just a point. So in the map, is, as we can see from left side, is the location of intersection on the roads. Then for this case, for this zone, I'm trying to, like the image, to cut the zones into different pixels. So this is very uniformly. And then based on the location, we can assign which pixel has the intersection. If this is the intersection location, we can assign the value of this pixel is 1, and otherwise it will be 0. Then considering the intersection, we have 4 approach. So I will use like 4. So each intersection will have 5 pixel or units with value of 1. So you can, so in the center will be the center of the intersection, and the 4 pixel will be represented the 4 approach. So this is how to assign the information of points to the pixel level. Then we can also, for the roadway line, so we can identify which pixel has the roads crossing this pixel. Then we can assign the information of the roads to this pixel. For example, this is VMT, which is a vehicle miles traveled, which is instead of the ADT is traffic volume multiplied by the roadway length. in miles. And we can know, okay, this pixel has the ADT, which level. And if the pixel unit or these areas don't have any roads, then the value will be 0. So this is the case, how to assign the roadway line to the pixel level. And the next one will be land use or other information is with this information is actually is area level, which is we can see zone level. So for this one, it also is for this, for example, this land use is like each color represent a different type of land use, such as the residential area or like commercial area or industrial area, all this information. So firstly, for this kind of thing, we are trying to know the boundary of the zone. And then we can know which pixel is at the edge of the boundary. Then we can mask, so the area of the pixel. Then inside will assign the corresponding land use category. So this is the process to assign the area or zone level information to the pixel. So based on the 3 different procedures, we can assign the information in the point level, roadway line level, and zone level to the pixel. And then we can like follow the same model. Here, say input will be different layer. So each layer contains the information at the pixel level for each variables, such as if it's the location of the intersection or not, or like speed limit information or land use. So each layer have different information. Then we can do the process of convolutional, and then we can output the information as the same usually do. So here we test this example is by trying to use the all the Florida area. So for this one, we generate around 5,600 grids, which is 3 miles by 3 miles. And each grid for the CM model, we're trying to divide them into 100 by 100 units, which is in total will be 10,000 units. And we're trying to use the traffic data, roadway data, and the land use data. And there's 2 different models, like negative binomial model and the neural network model, which will use aggregated variables for the comparison. So you can see here, we use 90% data for the training, and the rest will be the testing. So for the negative binomial neural network model, we'll use 25 variables. And on the other hand, the same model actually is 17 variables, but they will assign to the 10,000 units with very detailed and high resolution. So why is 25 and 17 is because for the first traffic or roadway information, which is 16 variables, we will the same as same model and the traditional way. But for the land use, because for one layer, we can use different number to represent the category, land use category. And then so one layer should be enough to represent all the land use category, but for the traditional way, we have to aggregate into 9 different variables. So that's why it's a 25 versus 17. So with all this, we're trying to develop a model and to do comparison performance, like the MAE, RMSE, and means absolute percentage error. So the light green is the same model, and the rest will be the traditional way. So we can easily see from that by using high resolution data and the same model, we can significantly improve the prediction result compared with others. And also between the 2 traditional way, actually they are similar. So if we use aggregated data, actually there's not significant benefit whether use traditional statistical model or machine learning model. So this is 2 conclusions can be get. And also we're trying to use R-square to test the prediction versus true ground truth. So we can see the negative binomial model, we can find more scattered sports point, and the R-square is around 0.7. And then for the traditional AM model is similar, but they're concentrated for the line. But when we come to the same model, the R square will come to 0.85. So it's significant better than the previous two. So this is kind of advantage to use the deep learning model and high resolution data for the crash prediction in the micro level.
Yeah. Hey, Dr. This is Ken. Sorry to interrupt. I have a question. So you are trying to predict traffic counts at zone level, right?
Yes.
So I'm kind of confused, like how you mixed CNN and the other variables in the model. Like what is the label of your model?
Okay. So let me go back here. So this is structure. So the input, as I mentioned, is how we prepare the data. And the output will be just one value, is the crash count.
For each zone?
Yes.
Or for each grid?
So each zone.
Okay.
The same model will input all the detailed information is by each pixel or like grid or like thing. The grid and okay, so I think they're different like term. Like the grid will be the zone. It's the total zone.
Oh, okay. So in the next slide, you said there are total something like 10,000 grids, which means 10,000 zones.
No, 10,000 units. So grid is the
okay.
Yeah.
Okay, I see.
Yeah.
So those are like smooth grids. It's like a rectangle. It's
Yes.
not like a geographic zone.
Yes, yes. So it's actually I'm thinking that it's now we're trying to solve like because as you know traditionally the transportation the zones is very not unique or uniform. So we're trying to solve this problem like how can we apply the same model to the ununiformed zone? Yes. Now
Okay.
for this study I'm trying to is just to use the uniform with grid. Yes.
So then in the next step you need to map these zones to kind of sensors geographic zones.
Yes.
Or
Yes.
okay,
Yes. Yes.
I see.
Yeah. Okay. So is there any questions regarding for the micro level?
Yeah, so the question, so here you have a lot of extra variables, right? Extra inputs other than the CNN. Well, in the CNN map, you have 3 factors, right? The map have what's that? They have an
RGB, RGB,
intersection segment and what's that? The
zone.
zone land use, right? And
Yes,
you
yes.
have also like segment level information, like how many lanes at each segment, how you kind of aggregate this information with the CNN map extracted information.
So the previously I said the point or the segment or land use or the zone is just 3 data aggregation level.
Oh, okay. I see.
For example, the point will be the intersection, or you can say the roundabout. Right? It's just a point information, and this line is I use the VMT like traffic is the example, but you can also to process this data for the speed limit or like roadway type.
Number of lanes.
Yes, yes.
So
yes.
those information gonna be integrated into this graph, like pixels, like
Yes.
as color, or?
I use the value. Here is a they show as the color, but it's actually the value.
Okay,
But
I
for
see.
the same model, I will normalize it
I
to
see.
0 and 1.
All right. Thank you.
Thank you. Okay, I will continue. Then the second one is about method level traffic safety analysis. For here, we're trying to analyze the effect of driver's visual environment on the speeding crashes. So it's how many crashes happened within the driver's view. So it's what you can see while you are driving on the urban areas. So on the left side is the Central Florida location, and the red rows indicate the urban arteries where we're going to study. So for this study, we are trying to use the Google Street View because usually we can see what for Google Map we can zoom in and see what is on the street. Okay, so for this one, I was using the API to request the Google Street View images by 10 meters. So each 10 meters will get a Google Street View like here. So here this is the video. It shows the images recorded by the Google, like each 10 meters. So, and in total, for all the arteries, we are downloading around 15,000 images requested. While we are requesting, we have several parameters we are going to set. The first is the image size. Here we are using like 640 multiplied by 400 is the image size of the resolution. And then location is just the coordinate of the point, which location you want to request. And the FOV is the field of view. Like, so it's like from the camera, like what's the angle of the, you want to request of the view. So it's larger, you can get more images or like areas you can see from the, so here where you are using 60 is for in previous study, they say 60 can represent the driver's field of view. And the heading is just like what's the, so because Google Street View, you can provide the view like a 360 angle, and also like for the top to the sky and bottom to the ground. All the images you can request, but heading is say which direction you are heading corresponding to the true north. So for example, here, if the road is just exactly to the northbound, so the heading will be 0. And if it's opposite is southbound, the heading will be 180. And if it's eastbound, it will be 90. And opposite will be 270, etc. So will be based on the direction of the roads to capture driver's visual view. Then the pitch is to see the rotate of your head. So pitch, for example, 0 is just you see horizontally just along the roads. So if the pitch will be 90, means you are looking to the sky. And the pitch is -90 is to the ground. So with this setting, we can download or request the Google Street View to represent driver's visual environment. And then we're trying to use the deep neural network image clustering to cluster what's the object along the road. And here you can see we can identify the trees, how many pixels is the trees, how many pixels is grass or the roads or the sky in the things. We can identify it. And on the other hand, we can, by using another deep neural network, is to estimate the depth based on the molecular camera. So this is because Google Street View actually provides you just one camera, and we want to use it to estimate, for example, for each pixel, what's the length or depth from the street we can get. And so based on this clustering, we can to calculate like how many pixels, like what proportion of pixels is trees on the driver's view, and how many is like buildings or like things. Because previous studies say if you have more trees in the driver's view, actually can impact driver's speed choice. And also we can, based on the different pixel or proportion, we can calculate the complexity levels. So if more elements in driver's view actually can reduce drivers like react time for the emergence. For example, because drivers will handle too many things and to react, they fail to react. So based on the depth or the pixel, on the other hand, we can use in the 3D cloud points by our inverse projection process actually we can get really in the real world by 3D point cloud to get the real X, Y, Z location. So for example, the trees, we can know from the cameras, the location, what's the distance from the trees to the camera location. And also we can know the tree's location to the roadway edge. So then based on that, we obtain like along the roadway, how many proportion is the trees, and also the trees is 30 meters away inside within the roadway. These also can be our variables. So here, as I mentioned here, we get the proportion of trees in driver's view and the proportion of roadway with trees within 30 meters. So actually so this difference is that, as we can see from the image, is that the proportion of trees in driver's is actually when I'm driving is the impact of the canopy, which is the shape of the trees. And on the other hand, is the proportion of roadway trees is that the roadway length with these trees. So they're kind of different. And so then the right side is illustrate the flow chart of the data preparation. Is we prepare the database base map to get the direction of the roads, and then get the coordinates of point by 10 meters. Then we will request the images by API, and we are doing clustering estimation to get different variables to reflect driver's visual environment to calculate in the following steps. Then we're trying to use the crash count and to do analysis. So we can use the statistical model for the analysis to identify the effect. And on the other hand, we can use the machine learning method to do the prediction. But as you know, like previously, the machine learning can provide a good prediction, but it's hard to explain the result or identify the effect. So for this study, I'm trying to using the XGBoosting, which is a tree-based ensemble model. And also I'm trying to use the shape value to interpret the effect of variables locally. So, and globally. So globally is trying to get the global importance of each variables by get the mean absolute value of each variable. So we can see, for example, the VMT, which is traffic exposure, is the most important variables, because you have more traffic. If you have more traffic, that means you have more crashes, which makes sense and reasonable. And also we can see the 4 variables that reflecting, which reflect driver's visual environment, like the proportion of buildings or roadway length with trees or proportion of trees, and the complexity is actually relatively important variables as we can identify it from globally. And then we can see the impact of the variables locally, and the higher value, here the red means the higher value of the variables, and it can be identified to be negative values effect on the crash, and also positive effect on the crashes. So we can also plot the scatter of the shift value to see what's exactly the effect of the variables. So you can see firstly is the proportion of trees. We can see most of them has the negative effect on the crash occurrence of speeding crashes. But so firstly, if we see a globally value, maybe just negatively. But then if we see detailed locally, we can see the magnitude of the effect will reduce with the increase of proportion trees. Then it will get increase, like has more negative effects within more proportion of trees. And also the proportion of roadway length with trees has a negative effect on the speeding crashes. As I think in your experiences, if you have more trees along the road when you drive, you are feeling like when you drive at high speed, you are more likely to say, okay, you are speeding, or you feel your speed is very high. So then you tend to reduce your crash. And for this finding, we can suggest, like if we want to really reduce the speeding crash, we can have more trees along the roads. And actually, this is one of the countermeasures recommended by the design manuals from the US Department of Transportation. And also we can see from the right bottom, we can see if the driver's visual environment is more complicated, it will result in more speeding crashes. So this is opposite. So in that case, we can evaluate the complexity and trying to reduce the complexity along the roads. So this is a kind of study trying to use computer vision and Google Street View and explainable machine learning to understand the driver's visual environment on the speeding crash occurrence on the meso level, and how to guide us to do the geometric design along the roads. Yeah, if you have any question, let me know for this part of meso level. Okay, so if you have more questions, just let me know in the end, and I will continue for the macro level. So the macro level is actually for the practice is when trying to predict traffic in real time to see if the crash risk will increase in the following 5 or 10 minutes. So for example, because we can capture, because if a crash happen, maybe due to the traffic turbulence or speed is variance, it can increase the traffic risk. And usually we're trying to use like a speed or volume or the variables to predict like whether it's highly likely we have a crash happen. Then we can use some technology such as the VSI, variable speed limit, to harmonize the speed. And also we can use some like warning sign to send a warning for the upcoming drivers to let me be more careful. And also we can use the signal timing to adjust the signal timing to provide more green light to harmonize the coming traffic. And it's also like recently we have like connected vehicles. You can also send warnings to specific drivers or vehicles. So usually, as we can see in the pictures, if a crash happens, we usually try to predict while we're using the upstream two detectors, downstream detectors, and we use different variables together to predict if a crash happened on the between. So in total here, I illustrated the 24 variables. And so the crash happen or not is actually the 0-1 problem. And we usually classical logistic regression is usually used. So actually for this 0-1 problem is also applied, like for example, in a bank, you apply the credit card. So a bank have to make a decision that you approved or not. This is also a 0-1 problem. And also like a bank in fraud detection, whether is a fraud for the transaction is a fraud or not. They can also is a 0-1 problem. So it's not for here for the traffic safety, but also in the other field has a similar problem, I think. So here is the example we can see. So usually we aggregate for the traffic information with 5 minutes. And but actually if we see the crash cases, like traffic has crash cases compared to the non-crash cases is very rare. As you can see, this example is like SR48, which is in Central Florida. So on the right side is our university, like University of Central Florida, on the east side of the Orlando. And on opposite is like University of Disney is on the west side of the Orlando. And so SR48 is actually called the East-West Expressway. It's connected to the east and west areas, and it is a very important road. So in total, it has 20 miles length, and we have 50 detectors. So during the one year in 2017, we obtained around 625 crashes happened on the SR48. So if we compare the crash and non-crash cases, we'll get 1 versus 11,000 cases that don't have the crashes. So it's very, very rare. So if we want to predict crashes, so for example, logistic regression, and trying to use all the data, so logistic regression say, no, there's no crash happened. So it's hard to develop the model because it will be, say, the model will tell you, okay, there's no crash, then it will give you a very high accuracy. But actually, and you cannot even identify one crashes, then your whole model doesn't work. So there's a traditional method to balance the ratio is trying to reduce the non-crash cases by using like random select or case control to make a ratio like 1 versus 4 or 10, etc. This is a traditional way method, and for this method, there's one disadvantage is that we are losing a lot of non-crash cases information. So in this study, I was trying to introduce like as the opposite. It was we're trying to oversampling the crashes and then to do the data balance. And so in deep learning, there's a very recently famous method is the generative network, which can learn the attributes of the raw data and trying to generate the similar things like this. So for example, in the picture, we can learn the pictures from the left side is like a coffee with a cup, and then by using the neural network, we can then to generate like this kind of image as close as possible. And so for this GAN model is proposed by the Lan Godflow in 2014, and it's become like generate new things very efficiently. So here in the following, I will introduce like how can this structure applied for the data generation for the crash cases. And also before the generation, we'll also test the correlation of different variables obtained by the upstream and downstream detectors. So we can see if the same variables such as the traffic volume, actually they have a very high correlation if they are in the same variables and at different location. But on the other hand, for the same location, like the upstream detectors, like speed or the volume, they are also a very high correlation. So in that case, if we just try to input the data like a one dimension, it's hard to capture this kind of correlation. So before we do the data input, I transfer the data as a 2D dimension. So in the same row is will be the same, the variable at the same location. So first of all is downstream location with different variables like volume, speed, all the things. And also for the same column will be the same variables, but at a different location. Then we can apply this convolutional neural network to learn and to capture this correlation. Then we can apply kind of the GAN model. We can propose the convolution GAN model, try to generate the more crashes. So here, so the process is like this. So we will have the training data set, like a matrix, and for the generator, we will first generate some noise, and with the input with the same model, we can generate a fake crash data. Then both of them will input as a discriminator, and that here is trying to tell if it's true crashes or not true crashes, and then we'll feed back to the generator. So it's most like the process is like, for example, if you just started to learn how to paint, and on the other, and you're trying to paint a very famous pictures like by previous artist, And then there's another judger is trying to judge what your paint and the famous paint by the like artist. And at the beginning, I think your paint is not good, so the judge can easily to tell which one is yours and which one is the famous one, and it can give you feedback, and you can learn and gradually improve your painting ability. And on the other hand, the judge is because it's also learn and to also improve his ability to identify which one is yours and which one is the famous one. So when the interaction process, both of you will improve, and then finally your generator will very close. Your ability will very close to the famous one, and it will be very hard to tell if the judges didn't improve stuff. So if the judge is very good, it maybe can tell, but it's very close, already has been very close. So this is the whole concept of GAN model itself.
Sorry, quick question.
Yeah.
When you say you are generating a crash, do you mean generated geometric information of the road or weather condition, or the type of crash, rear end versus angle, whatever?
Yeah. Okay, so it's a good question. So actually, I'm trying to generate the corresponding information for a crash. For example, the geometric, as you mentioned, or like a traffic information, traffic condition, if a crash happened.
Okay, I see.
Yeah. Yeah, thank you. So this is kind of architecture I developed to generate the data, which will include a generator, and on the other hand is the discriminator. So for this process is kind of so the discriminator is just an opposite process to the generator. This is the process, and also this is the method we proposed trying to generate the crash cases. And also there's a previous other method is called, for example, SMOT, is SMOT sampling method. So it can also create the minority cases by using k-nearest neighboring. But for this one, our input will be just one dimension vectors, and so not like 2D dimensions. So it's hard to identify the upstream and downstream correlation. So compared to our like convolutional GAN model. And also we compared with a random like undersampling method, which is undersample the majority like non-crash cases and for the develop our model. And for our testing, we get crashes is a 1 year data in 2017, and the crash data will be around 6,625, and we divided them into testing and training. And for the training data set, we'll do the, for example, if we want to do the oversampling, oversampling the ratio is 1 versus by 5. So we're trying to, based on the 400 crashes, we're trying to oversampling like around 1 million. 1 million data. And the opposite is trying to for the undersampling is we're trying to reduce the non-crash cases, and the random select get around 2,000 non-crash cases for the model development. So you can see if we use the oversampling method, what's the difference like between oversampling and undersampling, like how many data we can apply for this case. And this is some like plot of the distribution, like the ground truth crashes and the generated data. So we can see it's very smoothly follow the distribution of the original data. But for the SMOT, because it's like curious, it's always like follow the trend, but it's not as smooth as the GAN model. And also for the random select, so if the data is very like distributed like uniformly, it can also random select and follow the trend. But if the data has noise, the random select will randomly select because so it's hard to follow the distribution. So this is the like a comparison of the generated data by the different method. Then, based on the different method, by using the question and non-question, we apply different model to the comparison, like a logistic model, SVM model, like a normal like a neural network model, and the SAM model as well. Because we actually our outputs can be like a 2D matrix, as I mentioned. So in general, we can see is that the machine learning method is significantly better than the logistic, like a traditional way. And so traditional way, like a lot of papers, we can reach up around like the sensitivity and so, okay. Sensitivity is like the proportion, like true crash can be identified. So how many crashes you can really identify. And on the other hand, specificity is trying to say if there's no crash, you can also identify it's not a crash. And we can see from the logistic model, it tells us like around like 70.75 and to 80, which means 75% to 80%, like we can identify like for the crashes can be identified. So, but for the neural network, we can significantly improve like to the like 80 or 85 to 90. And also, for the data by the convolutional GAN model, we can provide the best result. We can consider the performance. So this is to validate our data generation method. And on the other hand, if we just use the logistical regression, there's no significance between different data set. So this is what we do for the macro level to balance the data for the crash prediction. And in conclusion is that actually within the adverse of detector method, we have more and more data. So it's our challenge or the chance to how to use the deep learning method and leveraging the high resolution data to provide better or accurate crash prediction and to enhance the traffic safety and by like a ITS control or planning or like a roadway geometric design. And although the machine learning can give us better prediction, we also need to carefully select the appropriate method and also to balance the accuracy and the interpretation. So how to understand your effect, the variables, is also very important. So here is the end of my presentation. So I would like to take any questions if you have. Thank you.
Yeah, Dr. Cai, yeah, this is Jidong. Can you hear me?
Yes. Hello, Jidong.
Yeah, thanks, Dr. Cai. Yeah, very interesting, very great presentation. I have two questions. I can only ask one, but if no people ask a question, I can continue. First one, Dr. Cai, can you go back to the slides before this one? Talk about the sensitivity and the specificity. I want to ask, when you define this, is that based on true crash, or is based on true crash plus the generated crash by the GAN model?
Okay, yeah, it's good, very good. So actually, we compared both. So it's a synthetic crash is generated by the GAN model.
Oh, I see.
And the real crash is the true crash. So as you can see, if the data is generated by the GAN model, we can get slightly better result, but they are very close. So which also validate our data generation process is very close, can generate the data responding to the true, very close to ground truth. Yes.
Sure. Oh, sorry, I missed that. But the next question for specificity and AOC, why is no reporting from real crash?
Let me see. Oh, you mean here?
Yeah.
Let me think. I need to recall. Specificity. Because for this one, specificity is trying to measure like a non-crashes. So it's like how many non-crash cases is identified non-crashes. So our generation is trying to generate the data for the crashes. So with specificity, we just have the real data. Yeah.
Got that.
I think some misleading here because I should put this value to here. Then we like, I think the column is misleading. Yes, the question. Yes.
I see. Sure. I have another question, but I can wait to see whether people have other questions.
Yeah, sure.
Sure. Yeah. Maybe let me continue, Dr. Cai. My next question regarding that's the R square page. Can you go to that page? Yeah, this one. So on the, I think the x-axis is observed, the y-axis is predict. So if you look at the left graph, the R square is about 0.7, but if you look at the relationship y equal to 0.99x, so which means predict crash very close. Observe the time 0.99 equal to predict. So that means this is unbiased. Even R square is not that high. But if you look at the right hand CNN, R square is high 0.85, but y equal to 0.83x. So does that mean this predict actually consistently under predict, or maybe mean this is a biased prediction? Is my understanding correct?
Yeah, I agree. So I think it's like this way. So if we think the slope, I think you mean slope.
Correct, slope.
It's for the next binomial model. I think it's because it's more follow because our crash count is like a non-negative count, like 1, 2, 0, 1, 2, 3, 4. The structure of next binomial model is more likely to capture this kind of data distribution somehow. So I think it will give you better unbiased things. But for the same model, yes, because I just use MAE as a mean absolute value, maybe some values will give us the some underestimated. Yes, they do have this. But for the next binomial, we can see it's very sparse. So that means for some cases, it's very unlikely to predict very well. But yeah, so that's a case.
I see. Oh, actually, Dr. Cai, you make a good point. Maybe you can also mention this. I don't know. Maybe you can calculate confidence interval, so you can see CN they have much narrower band. So basically, they can also do much centralized, much concentrated forecasting. Yeah, Dr. Cai, thanks a lot. I learned a lot. That's all my question. Thanks.
Thank you, Jidong.
Hey, Dr. Cai, can you hear me?
Yes.
Yeah, this is Chifan from the University of Alabama. Actually, I have 2 questions for your great presentations. The first one is a little bit tricky. So I wonder, so when did you collect those Google Street View pictures? Do you remember? When did you? Because recently the Google Street API, they changed the API charging policy, actually the pricing policy. So I collected.
Actually, I just do it this year, but
Oh, okay. Because what I did is I tried to collect some Google Street View pictures on some rural Tuscaloosa, no, rural Alabama, I think state routes. Then I reached the limit, it just started charging me, So I just wonder.
You can use different accounts.
Yeah, that's true. That's what I'm thinking about. Okay, second question is a little bit more general. So I wonder for the GAN, the third paper, you're talking about the GAN technology. I wonder if just forgive me if I missed some important information for this GAN. So you try to increase the data set using the GAN technology to generate some more crashes, or you said it's like synthetic crashes, because those crashes are kind of like rare events and it's a little bit biased in the data set. Am I understanding correct? Or
yes. I'm trying to generate more crash cases. So I think generate more crashes is misleading. Actually, I'm trying to generate the traffic attributes corresponding to the crashes.
Okay. All right. Thank you. Yeah, that's great. That's great presentation. Yeah, I appreciate it.
Thank you.
Hey, Dr. Ted, do you have a personal machine to run all of this, or you're using cloud computing?
We both. We use our lab has like good computers to process it. So yeah.
I see.
Personal one, yes.
Hello, Professor Ted. Can you hear me?
Yes.
Oh, yeah, it's Wendy. I'm from Cadsea. So I have a question about your CNN methodology. So you encode every information into the pixels or the image.
Yes.
Right. So is that because some information, probably some extra information may be useful, but very hard to encode into pixel or image related information. And by the way, from the literature, there are people can put such information into other kind of encoding, but not at the first level of CNN, but probably the higher up, and just do some concatenation with image results from the lower levels. So they can do some tricks there to put the different kind of information together, and send to the higher level. So have you tried that, or maybe you have thought about that? Probably they have limitation or problem with that. So I just want to know.
So are you referring the first paper, right, Wendy?
Yeah. Mm-hmm.
Yeah. So actually, maybe for the understanding your question, actually our same model is not, the input is not learned from the image. Mm-hmm. So we just I just mimic the image pixel like idea, because if we give image, so we can cut them like 100 by 200 like a pixel, right? Or even you very closer for the cut the image. For my approach is the same thing. So I just use the pixel idea, but actually the data is not from the image.
Right. So what I'm trying to say is that if you the bottom level of CNN is a pure image information, right? So if you go up and up at the CNN structure, so the higher level would be more conceptual, right? So about the object attributes of the stuff in the image, right? So I think probably at the higher level, it's a better place to take advantage of the other non-image information. So that's.
So you mean that it's just learn one same model, but in the end, maybe we can add some other information.
Right. So for example, the number of names, you you mentioned that, right? So that's a non-image information, right? So I'm just trying to see where is the best location to use that information. So because your CNN has some levels, right? So I don't know if it's a good, best idea to just to encode them at the bottom level, because the bottom level is just pure image information. Right?
Yeah. I understand your point. So I think maybe, so first of all, for the number of lane, for example, here is the VMT information. Because for one zone level is, for example, county, or like for this zone level, you can get, like, for example, the proportion of a number of lane is 4 lanes, or proportion is the roadway number is 4 or somehow. But you don't know for each location in this county, so where is the road has a number of 2 lanes, two lanes road, or where is the 3 lanes. But for the same, for the bottom level, I think we can input this information. But I think also your suggestion is a very good idea, is that we can use both. So first of all, we can use the number of lane from the bottom level, but in the end, maybe we can add other features at the end to aggregation, as you mentioned, a higher level,
right?
Together and to do the crash count prediction.
Yeah. So, for example, if there's at the crossing there's a stop sign, so I guess probably at the high level it's a better location to use that information, like a stop sign, or is there traffic lights, or these kind of things, right?
Yes, I agree. Yes.
Yeah, that's an interesting part. Thank you.
Thank you.
Any other questions? Okay, if not, we will stop here for today. I want to remind you to pay attention to the group chat where Mr. Su Wenyong shared information regarding the PE-PDH credit. If you are from civil engineering area, you want to get the PDH credit, please contact Mr. Su. The email information is shared in the group chat. Yeah, and this is a great presentation, and I personally learned a lot from here. And to be honest, my knowledge level is not there enough to follow very well. But I think there are a lot for myself to learn, to catch up, and that's a great example of using deep learning technology for real world problems, and I think it's very interesting. Thanks a lot, Dr. Cai, and we hope to have you in our room in the future. And also thank you everyone for attending this event. We will stop here for today and look forward to seeing you all in our next event.
Yeah, thank you, Dr. Zhang, for the invitation. And just one mention is, like, if you have any question, just let me know through the email, or you can reach me with WeChat or LinkedIn any way you prefer. Yeah.
Cool.
Thank you.
Awesome. Thank you, everyone.
Hey, Ken, sorry to interrupt you. Yeah, maybe do we have some time? I can talk about Cadsea membership.
Yeah, sure. Sorry. Yeah, go ahead.
Okay. Yeah. Thanks, everyone. Ken, can you hear me? I think that's yes, right?
Yes, I can. Yeah.
Sure. Yeah. Everyone. Yeah, my name is Jidong. I think let me share some information. So first of all, I'm the vice chair of this Cadsea. I work with the many volunteers together. As Richard talked about in the beginning, we want to build up the community, and also the best to develop that is we grow our group or the pool of the members. So let me very quickly, maybe less than 2 minutes, to repeat what I said before, why people should consider this, and what's the current status, and what's the next step. I think a benefit of Cadsea is after you join the Cadsea, you do not need to pay the actual cost to attend all the great presentations such as today for the next 12 months. And also for all the speakers such as Dr. Cai, we also can enjoy the complimentary membership for 12 months. So Dr. Cai, I will reach you separately. I think one of the most benefit is like the Richard side. We are currently develop or maybe considering to develop to release the new program. Want to hear the people's thinking, especially from the members. So that's the reason I strongly encourage everyone to think about if you are in this data scientist area, or if you would like to be moved to that area, or it's just your hobby, you want to learn more data science, please contact us. The website is cadsea.org/membership, so you can find a lot of information there. Second, about the current status. So I think we announced the Cadsea membership is ready and open to ready to accept the membership application. As far as today, I think we have about like 2,000. I'm so glad to see several new members join during the last week, even during the weekend. So please consider and please join us. The third topic is about the next step. Yeah, as one of volunteer, I work very closely with other volunteers, including Nan Yun, Hong, Lei, and Kenny. We also work very close with our IT development team, led by Yue. We want to continue improve our process. We know we are pretty new organization and also new program. Right now, we are considering to make this process more streamlined, such as we plan to kind of generate a welcome letter and registration receipt. Hopefully in the future, we can send out almost simultaneously when people register that. We are also thinking about put a way to notify members if the coming events coming out, the future event. So please also let us know any suggestion, all the suggestion recommendation are welcome. So that's all. So want to say, please, please come out, please join us. Let's build up the Cadsea community together. Go back to Ken, thanks.
Thank you, Jidong. Yeah, that's very important. Thank you for making this call. Yeah, we do need a lot of volunteers to join our team to work together to make this program more successful. And yeah, feel free to reach out to any of us if you have interest. Thanks a lot, everyone. Look forward to seeing you all in the next event. Bye.
Bye. Yeah. Thanks, Dr. Sa. Yeah. Thanks, everyone.
Thank you, everyone. Bye-bye.